Hey guys, the next thing we're going to actually look at is sum of the forces equals ma, just specifically in the x-axis. Now we're going to start using the full equation, sum of the forces equals ma, Greek letter sigma. Right here means sum of, we're going to add up, and your free body diagram is going to be incredibly important. So before we actually start on our example problems, let's look at our steps. First off, draw a free body diagram and then pick your positive and negative. I can't emphasize that enough. Please draw your free body diagram. It is the key to everything that you're going to do. Just like in kinematics, that your free body diagram is your variable bank, and just like in kinematics, you need to rewrite the equation, sum of the forces equals ma. That's a step you're probably going to want to skip. Please actually rewrite it. Then we're going to look at our free body diagram that we drew, that we picked positive and negative on, and we are going to use it to fill in the sum of the forces side of the equation. So first example problem that we have over here, we're going to do two of them. I've got a car driving along. It looks like the mass of the car is 1,900 newtons, and it's accelerating from a red light. The engine is going to apply 4,300 newtons of force. Let's go ahead and maybe get some numbers on here. All right, so there I got my mass and my force of push because the engine is applying 4,300 newtons of force. Looks like a little typo here to accelerate the car forward. Friction's going to resist with 680 newtons of force, and I'm looking to calculate the acceleration of the car. All right, now that I've actually gone ahead and I pulled all the information out of the problem, I had a picture already set up, and drawing a picture is always a good idea, and labeling the picture very well, it actually makes doing the free body diagram easier. It's not the free body diagram, but it is very similar. Next step, it's the first step actually in our listed steps here, is we need to draw a free body diagram. So I'm going to go ahead and do that. All right, so there's my free body diagram. This would actually be a good chance for us to review drawing free body diagrams. Whenever you're looking to draw them, actually think through some questions like we had talked about previously in class. Is something pushing the car forward? Yes, the engine is pushing the car forward. I labeled it FP. You could label it F sub E if you would like for force of engine. You could also go ahead and write that FP equals 4,300 newtons there. That's perfectly fine. In fact, that probably would be very helpful for many of you to actually write that. Just actually label it with the letters too. Don't forget letters there also. Next question, is the object on Earth? Well, yeah, it's a car. It's driving along on Earth. That means we have gravity, so force of gravity. Not the acceleration of gravity, 9.81, not the mass. Those are different. Remember, the force of gravity is going to end up equaling mg. Now, in this video, it's not going to be overly important. In Lesson 5, with y-axis, it's going to be critical. Here, force of gravity going down. Normal force always goes perpendicular to a surface. So if the object is on a surface, you have normal force. If an object isn't resting on a surface, you don't have normal force. So we have normal force going up, and I drew it equal in length to the force of gravity because the car isn't accelerating upwards, nor is it accelerating downwards. It says here that we have something to do with friction because friction resists with 680 newtons of force. So I drew friction going opposite the direction of motion, coming back to the left for me. Force of push is trying to accelerate the car forward, friction going backwards. And notice that I drew the length smaller because the force of push is 4,300 and friction is 680. This is not balanced out. This car is not going at constant velocity. It is accelerating, so the force of push should be winning. Now my next step is to write down positive and negative, and it honestly doesn't matter which way you choose as long as you're consistent with yourself. I'm going to call to the right positive and left negative, and the only way I could get that wrong is if I called both ways positive or both ways negative. I'm going to call up positive and down negative. Once again, the only way I could get that wrong is if I called both the same sign. Step number 2, rewrite the equation. Now you're going to see me a lot of times actually writing either an X or a Y, trying to label where the sum of the forces is being done, because we do a sum of the forces in each axis individually, and here we're just doing the X-axis. How do I know this is an X-axis problem? Because the car is traveling in the X-axis and we're looking for the acceleration of the car. The car's going left and right, so the car's accelerating to the right here. That's in the X-axis, so this must be an X-axis problem. So sum of the forces equals ma, and I label it with an x-axis kind of over the top. Now I'm going to use the free body diagram to fill in this left-hand side of the equation. This is why the free body diagram is so incredibly important. And quite literally, I'm just going to read off of the x-axis, because that's what I'm dealing with, on my free body diagram. It looks like I have a positive FP. FP is going to the right, so I'm going to start out by writing FP, and I'm going to leave it positive. You can imagine a little positive sign out in front there if you would like. Some of the forces means I'm going to add them up. So I'm literally adding here, right? So my next one is going to be the force of friction. Looks like it's going back to the left. Force of friction is negative. So I'm going to write minus force of friction. If you need to imagine here, you could say this is plus a negative force of friction. That doesn't matter. And this is all going to equal ma. A lot of times I get questions, how do I know what goes on the left-hand side of this equation? What is the sum of the forces? All you do is you look at the free body diagram that you spent time on, and you literally read off what's going positive, what's going negative. Now I can go ahead and fill in these variables, these forces and the mass, with what numbers I have and work the algebra for the acceleration, because I know what FP is. FP is 4,300. And I know what the force of friction is. The problem tells me it's 680. That's going to equal the mass on the other side, just filling in the equation with numbers. The mass was 1,900, and that's times the acceleration, A, which is what I'm looking for. And after working the basic steps of the algebra right, I combine these two terms, subtract 3,620, divide my 1,900 over, trying to peel things off of the acceleration. So 3,620 divided by 1,900 gives me a acceleration of positive 1.9 meters per second squared, acceleration unit meters per second squared. And notice that it turned out positive. It could have turned out negative, but I chose to the right positive, and so I would expect my answer here to turn out positive as well, because it is accelerating to the right. All right, in my second example problem, looks like I have a kid on a sled here. Maybe it's winter time and we're in Georgia, so maybe this is the one day out of the year we got a little bit of snow. And somebody is pulling the kid along on the sled. Sled and kid have a mass of 39 kilograms, as you see here in the problem, and is being pulled along with 19 newtons of force. But the 19 newtons of force evidently is not enough to actually cause the sled to accelerate forward, nor is it enough to cause the sled to continue to go at a constant velocity. In fact, evidently, this 19 newtons of force is weaker than friction because the sled is decelerating at a rate of 0.98 meters per second squared. Now let's start out and let's just do a free body diagram like we know we're supposed to. Starting out, is there a force pulling the sled along? Yes, you could label it FP, or I know it's a rope here pulling it along, so I labeled it tension T. It's going to work out to be the same one way or another. That's 19 newtons of force. Also, we know that there is friction fighting and resisting. Now I'm going to draw friction to actually be larger than the tension. Main reason for that is because the sled is decelerating. Friction is winning right now. We were going some velocity and friction's actually slowing us down. What velocity we were going actually does not matter whatsoever. Is this object on Earth? Well, of course, so that means we have a force of gravity going down. You could label it Fg for force of gravity or weight because they're the exact same thing, one way or another, mass times 9.81. Also, the sled is on a surface, so I'm going to draw normal force going up here, and I'm going to draw those to have the exact same length because the sled is not accelerating up into the air nor plunging down to the depths of the Earth. Pick positive and negative. I'm going to choose to the right positive again, left negative, up positive, down negative. All right, now the question A says calculate the magnitude of the frictional force that causes the deceleration here. Now in the past, whenever we were looking at friction, what we could say was, hey look, we're traveling at constant velocity, so the tension is the same length as the force of friction. So if we know the tension, 19 newtons, that must be the force of friction, but that's not the case here. We are slowing down 0.98 meters per second squared as our deceleration. So I actually can't say these two are the same. They're not. Friction's bigger. Look at your free body diagram. That's why focusing on the free body is so important. I actually need to work through an x-axis problem. So I label it, I'm going to work through the x-axis because that's where the force of friction actually is. It's in the x-axis, the one that goes horizontal, not the y-axis, the vertical here. So x-axis, sum of the forces equals ma, and I'm going to now read off my free body to actually write those forces in. Looks like I got a positive tension, so I'll do a plus T over here, and a negative force of friction. So negative FF equals MA here. Let's go ahead now and substitute in what numbers we know. Now, I purposefully haven't written the acceleration yet. I'm just going back through. We know the tension is 19 and tension's going positive. Force of friction is what we're looking for. We don't know it yet, so I left it force of friction there. It's going back negative. Mass, total mass, it told us, was 39 kilograms up here. And then it told us the sled decelerates at 0.98 meters per second squared. And you might be tempted to write just 0.98 here, but we can't. We have to write negative 0.98. So let's talk about that. Which way is the acceleration going? Now, accelerations don't go on the free body diagram, but the acceleration vector is actually going in the same direction as friction. A equals 0.98 meters per second squared, but it's going back that way on our free body diagram, or on our picture back this way. Remember, a positive deceleration is the same as a negative acceleration. Friction is winning, so this deceleration should be negative. Well, now I've got everything set up in my equation. I can just simply work the algebra. Now, working this algebra over, right, I multiplied these two numbers, negative 38.22 because it was a negative 0.98. I subtracted the 19 to the other side, so now I have negative 57.22. And you might say to yourself, hey, I'm done, I've got the answer. Well, not yet. Look here, you got a negative force of friction equals a negative there. So let's multiply both sides by negative 1 to get rid of that negative sign over there, and then I actually get what my answer is here. The force of friction must equal 57.22 newtons, or if we were to report this in correct significant figures, looks like up there in my problem I have two significant figures everywhere, so 57 newtons would be my final answer there. Now, part B says, hey, let's actually calculate the coefficient of friction between the sled and the ground. And I remember back from lesson 3, our equation where we were dealing with friction in particular and trying to calculate the coefficient of friction is force of friction equals mu times normal force. So this is like a question from our friction lesson in lesson 3, I believe. So here, force of friction equals mu times normal force, and I now know the force of friction. I'm looking for mu. The only issue is I don't know the normal force. So now I've got to go somewhere to figure out what my normal force is. I use the unrounded force of friction here because I'm bringing it down. I'm looking for mu. But remember back from lesson 3, since this sled isn't accelerating up in the air nor plunging down to the depths of the earth, the force of gravity and the normal force are exactly the same. So if I calculate the force of gravity in this case, in particular, it is the same as the normal force. Now the equation for the force of gravity is Fg equals mass times 9.81. So I'm going to do a little bit of side work over here. Go ahead and write that down. And Fg now equals 39 times 9.81. And that gets me the force of gravity. Sorry for that 8 not working out. There we go. That gets me the force of gravity, and that will be the same as the normal force. All right, now I can just simply work the easy algebra, divide over my 389.59 over to the other side, and then I'll have my mu. So the coefficient of friction between the sled and the snow or ice, whatever that surface was there, turns out to be around 0.15, and that makes sense, well less than 1. Around 0.1, you're looking at a pretty slick surface.